Okay.
Thank you.
Yeah.
Stressful there in the end.
Oh, we got it.
We made it.
Well, thanks everyone for joining us
Thanks.
today. It's a pleasure for me today to introduce Dr. Frances Rivera-Hernández. Dr. Rivera, she is an assistant professor at Georgia Tech right now. We actually go back quite a long time, and I just found some photos from our adventures in the Andes about 10 years ago when she was an undergraduate student at the University of Wyoming. And I was a younger assistant professor at the time. Frances joined our group in doing fieldwork in the Puno Plateau of northwest Argentina. As you can see, I like to think that this was the beginning of her career because it looks like Mars. But
Yes.
some water, right now. And we spent actually a fair amount of time out there in pretty remote areas. And this is another kind of great photo of a party that we have. The only single human we found out there who has not seen anybody for like a year or so. He's yeah.
Yeah.
And he actually decided to do a party for us at the end before we left, and he cooked a goat for us. And that's the ghost right there. And you can see right the shape of the goat. The head was hanging somewhere.
Oh my goodness. So traumatic. I still have it. Poor goat.
So Frances has an incredible actually career for being such a early career young faculty. She's been so successful, and in fact I feel like it was just yesterday that we overlapped, and she was an undergraduate student doing a research project with me and a colleague of mine, Mark Clements, and before I know, I turn around and she's this amazing established young faculty who is doing incredible things. So she graduated in 2009 with a double major in astronomy, astrophysics, and geology from the University of Wyoming. Then she moved to the University of Washington to do a master in Earth and Space Sciences, and she did remote sensing on Mars. And then she moved to UC Davis for a PhD, where she graduated in 2018. And then between 2018 and 2020, she was a postdoc at Dartmouth College, and then started her assistant professor career in January 2021. And since then, she already has an amazing group made of 3 PhD students, 2 undergraduates, 1 postdoc, 6 funded NASA projects, 2 as a lead PI, 24 published papers, and so forth. And she's been also a leader in several, of the geology kind of team for the rover mission. So without further ado, welcome.
Thank you so much.
Let me make sure to get this correctly.
Great. The first time anybody has had pictures of me from like 11 years ago. It's great. I didn't realize those existed. Like I told you, just like a memory. And I will say that almost every single image that I will show is the real pictures of Mars. So, but I will tell you what's Earth and what's Mars. But yeah, hi everybody. Thank you so much for coming today. As Barbara mentioned, I'm Dr. Frances Rivera-Hernández, and I'm indeed an assistant professor at Georgia Tech. I've had the chance to, this is actually the first time in Tucson, and it was been a great day, and I've had a chance to talk to a lot of you. But if we have not had the chance to talk, I'm a planetary geologist. For me, that just means I love doing geology in more than one planet, mainly Earth and Mars. And in most of my research, I study sedimentary rocks and terrains to characterize ancient and present environments on planetary bodies, as I mentioned, mainly in Earth and Mars, also, although I am interested in other planetary bodies. And I do this work to be able to obtain information on past climate and water availability, and to really think about whether these water environments that I'm reconstructing, whether they could have been habitable for past life. And again, this is work that I do for both Earth and Mars. And then if you want to follow me on Twitter, I like to tweet. My research is interdisciplinary. I commonly combine remote sensing, numerical analyses, and field studies. Again, I've had a chance to talk to you a lot about this today. A lot of my field work is in polar environments. This is a picture of me actually in front of a delta and one of these curly ice covered lakes that I studied for my PhD. I also do work in the Canadian Arctic and have been trying to apply some of this work also for the Neoproterozoic, thinking about snowball Earth. But of course, my talk today is Mars heavy, and I also do. I do a lot of work with the Curiosity rover mission. I am a participating or collaborating scientist on the Curiosity rover mission, and so a good chunk of my work is also focused on that. But I'll be talking about that today. Outside of research, I'm also heavily involved in multiple organizations that are helping to increase the representation of Latinx in STEM. And I've had a chance to talk with some of you about these today. These include Geolatinas, which is an international group of Latinas from all over the world, all sorts of disciplines. We kind of started with 4 people, and now we have like 300 members, something like that. We're quite active on the internet, so you probably have heard of Geolatinas. There's also Soles, which is a society of Latinx, Hispanic Earth and Space scientists. We also have a website for that. And then the Boricua Planeteers, which is a Puerto Rican or a group of Puerto Rican space and planetary scientists. Like I said, we have a online presence for all of these. So if you're interested in learning more, if you want to join or if you want to be an ally, I'm happy to talk more with you about that. Or you can just follow us and like and retweet our tweets. That's also okay. But enough about me. As the title of my talk suggests, today I'm going to be focused on research on how I've been working to reconstruct ancient environments on Mars, both from the grain to the landscape scale. And for most of my talk, I'm going to be focusing on some of my work with the Curiosity rover, where I've been working to use a grain-sized proxy that I developed to be able to interpret past environments on Mars. And then for the last 10 minutes or so, if we kind of get to that, the tech delays, I'm going to be focusing on some of my postdoctoral work where I was characterizing deltaic deposits on Mars to reevaluate the global ocean hypothesis for Mars. For both parts of my talk, I'm going to be talking about the Gale Crater or the Gale Crater region. Gale Crater is the home of the Curiosity rover, and it's located in the equatorial regions of Mars. And so here on the left is a orbital image of Mars, just kind of highlighting where some of the previous missions have landed. And Gale Crater is right here with the star. And just as a reference, the new Perseverance rover is all the way up there. And this is what Gale Crater looks like. This is a satellite image that's in black and white or grayscale, showing Gale Crater. And the star is highlighting the landing site for Curiosity. And in the middle of this crater, there's this massive mound of what we think are sedimentary layers that we call Mount Sharp. And it's actually the lower reaches of Mount Sharp that is the final destination for the Curiosity rover. And so, like I said, Gale Crater is it's located in the equatorial regions of Mars. It's also located in one of the most striking features of Mars, something that we call the Dichotomy Boundary. And so, and it's this feature right here. It kind of separates the northern lowlands of Mars that are younger and smoother from the more rough southern highlands of Mars. And there's evidence, geologic evidence, that liquid water once flowed from the south towards the north, pooling locally in Gale Crater and surrounding topographic lows in lakes and potentially an ocean. From crater counting, which is how we determine or commonly determine ages for Mars, we know that Gale Crater formed about 3.6 billion years ago, which coincides to a time on Mars where we know the climate was changing from one that was wet and potentially warm to one that was cold and kind of dry, which is sort of what we have today. And so this is something that we see from the geologic record. We also see that the alteration minerals on the surface also change, mainly from what we call clays to sulfates during this transition. And we actually see that transition in mineralogy in that middle mound of Gale Crater. And so it's possible that the layers of that mound record this climatic change from, again, wet and possibly warm to the cold conditions of today. Beyond that, from a habitability standpoint, Gale Crater is also a great place to study. As I mentioned, lakes likely formed in Gale and in the Gale Crater region. And we know from Earth that not only are lakes stable water environments for life, they also, the deposits of lakes are also really great at preserving biosignatures, particularly lake mud. And so because of that reason, lakes are a major target for Mars exploration. So if you ever wonder why we keep sending rovers to these possible Paleolake basins, that's why. And so just to kind of drive home a little bit of that, this is sort of NASA's plans for Mars exploration. This diagram is actually a little bit old now, but the Curiosity rover kind of falls here, which is kind of following the water and exploring habitability. And the new rover, just as a reference, again, we didn't even name it when we made this diagram, but the Perseverance rover is all the way over here. That rover is actually seeking signs of ancient life. But again, we're talking about Gale Crater. So you can imagine that there's an interesting, hydrologic and habitability story, and also climatic story here in Gale Crater, which is one of the reasons that I find Gale Crater and the region particularly interesting. But today, I really want to focus more on the hydrology part of that story. And so for the talk today, I have these two driving questions. For the first part, I'm going to be trying to address what environments are preserved in the sedimentary rocks in Gale Crater, and what does this imply about Mars paleohydrology. And then in the second part, we're going to go into the landscape scale, and I'm going to be addressing from geomorphology how much water was sustained in the broader Gale Crater region, where there are multiple lakes or a global northern ocean. And so for the first part, I'm going to be using data from the Curiosity rover. This is one of the many selfies for Curiosity. This is what it looks like. And I'm mainly going to be talking about data from one of the instruments called CamCam, which is actually the big eye of the rover there. And of course, this is a mission, and I have a ton of collaborators. I can't even put them all there. So thanks to them, and also the MSL team. And so the main mission objective for the Mars Science Laboratory, or the Curiosity rover mission, has been to characterize habitable environments on Mars from the sedimentary record in Gale Crater with Curiosity. And so here on the left is that orbital grayscale image that I showed from Mount Sharp, highlighting the landing site. And then here on the right is just that area sort of blown up. And this is kind of showing the traverse that the rover has been going. And it's actually quite old. The rover is actually all the way, it's already done this and has come back. And so it's kind of up here now. But one of the things that we've been able to see throughout this transect is the presence of grains that look like they were clearly transported by liquid water. And so one of the things that we want to determine is, what were those environments? In particular, since we know that, at least for Earth, water equals life, and we want to get a better sense for what liquid environments were present in the past. And one way to be able to determine past environments is by actually looking at sediment grain, particular sediment grain size. And so this is why I love sediment so much. The amount of energy, the size of the grains correlate with the amount of energy of the main process that transported the grains. And so you can imagine that if you were at, in a tidal flat that's dominated predominantly by mud and sand, because it's a low, quiet environment, you tend to have finer grain sizes. Where in more energetic environment, like a river, you might see larger grains. And again, that's because again, typically you can imagine that energy of process correlates with grain size. And then of course, in the sedimentary record, the mud and the sand from those tidal flats may get preserved as layers of mudstones and sandstones. whereas those river cobbles may actually get preserved in the rock that we call conglomerates, as shown here. And so by actually looking at the size of the grains and of course other sedimentary textures and structures, we can then determine what past environments were present in the rock record. Of course, for Earth, this is quite easy. You can just go out in the field with a grain size card or a hand lens. These days you can even bring a rock back and then dissolve the grains out and put them through a fancy machine to get really detailed grain sizes. And I also do some of that. But of course, on Mars, we can't do that. And so for Mars, we have to use images. And so because of that, the Curiosity rover actually has 17 cameras. And we use the images taken by these cameras to interpret geology, right? And so this is just kind of showing where some of these cameras are located. And actually the new Perseverance rover has something like 22 cameras, so it has even more cameras. The camera that we actually predominantly use to get a grain size is called the Mars Hand Lens Imager, or MAHLI for short. And we can actually resolve things as small as core silt with the highest resolution images. And actually the MAHLI camera, you actually can't see it here because it's located in the rover arm. And very similarly to when you take a selfie with your phone, you can't see your arm. Same thing happens for the rover. And you can even see the arm here, right? You can actually see the shadow down here. And so next time that you see a selfie for Perseverance or Curiosity, I always try to hunt down the shadow. But all those images are taken by the MAHLI camera. Curiosity actually can only take pictures, but Perseverance can also take videos. So that's been one of the major advantages of the new rover. And so typically coarse grains are well resolved in Curiosity images. And here are just a couple of examples. Here on the left is an image of a coarse sandstone. And then on the right is a conglomerate. Again, both of these pictures are for rocks on Mars. And in both cases, again, you can clearly see the grains or the clasts, right, depending on the image. And even this one, you can see that beautiful luster in that image. And it's really super clear. Same here for this well-rounded pebble. And so while we can see coarse grains in images, finer grains are harder to resolve, as kind of shown here. And so this is just a series of pictures for different types of rocks that we've imaged with the Curiosity rover. It even becomes quite difficult to distinguish, clay and silt to very fine sand. That transition is really hard for us to identify. And that's not only due to the limitations of the cameras, but how far are the rocks from the rover? And also Mars is really dusty. There's dust everywhere, and it's always a problem. And so because of that, we really can't distinguish typically, this sort of transition. And this, of course, is a problem for sedimentologists, as that transition is the difference between thinking about grains that are being transported in suspension versus grains that are being transported in traction. And that's information that we need to better interpret past environments on Mars. And so to complement the grain sizes determined from images, I developed a grain size proxy that uses geochemical data from the CAM-CAM instrument, which is a laser-induced breakdown spectrometer. And so this is what the instrument kind of looks like here. As I mentioned, it's located in the big eye of the rover, and it uses a pulsed laser to zap rocks and sediments that are 2 to 7 meters away from the rover. And it's the light that's created from the plasma at those spots that we then measure with a spectrometer to get at compositional information. And just to show you an example of what those little zaps look like, this is a picture of a rock on Mars, and you can see the zaps right there. It's kind of hard to look at here. It's just kind of to show you what they look like, and also how we typically take the measurements. And so we commonly do them in lines. So you'll do multiple points in a line, or we'll do a matrix like this case here. And so this is really common. And the reason that I'm able to connect the CAM-CAM data to grain size is because we actually know the size of those laser marks. So the size of where that laser hits. And so you can imagine that if you had the laser hit a rock that had grains considerably smaller than that laser spot size, say a mudstone, then if you move the laser spot, then what we measure is bulk rock composition at each of those spots. And so we see very little chemical variability from spot to spot. However, if the rock has coarser grains closer to the size of that laser spot, it's possible to hit individual grains. And so we do expect to see chemical variability. Of course, this only works if the grains have different composition, which we do know is the case for most of the rocks that we've been exploring. CAM does give us compositional data, and we have other instruments on the rover that provide information about the chemistry of the rocks. And so kind of like a grain size card, I've been kind of using this to estimate grain size by quantifying the amount of chemical variability between each of these spots for rocks. And I've been able to do that using a statistical parameter that's called the Gini index, which actually was developed for population studies. And I've repurposed it to quantify not variability in population or money and population dynamics, but to quantify chemical variability in this data. A Gini index of 0 means that there's no variability from point to point, whereas a Gini index of 1 means that there's complete heterogeneity between each spots. Due to time, I don't want to get into a lot of the nitty-gritty of how the numerical part of this works, but I have 2 papers where I go in plenty detail. So if you're interested, definitely check those out. And of course, I'd be happy to answer any questions that you may have about that. But for the talk presented today, we're interpreting low Gini index values as finer grain sizes and high Gini index values as coarse grain size. Using this technique, I've been able to determine the grain size for sedimentary rocks and Jezreel Crater. Today, I'm only going to be talking about something that we call the Murray Formation. And so here on the left is that same image with that area blown up here on the right. The Murray Formation is kind of highlighted here on the orange. And we encountered it at a location that we first encountered it at a location that we call Pahrump Hills. And from that location, we saw that the Murray Formation is dominated by laminated mudstones interbedded with sandstones. And the team interpreted this to represent deposition of rivers emanating from the crater rim, transporting grains and depositing them in a lake, kind of shown here. While we have explored a lot of the Murray, the most detailed study was at this Pahrump Hills site. Here are just some example pictures from Pahrump Hills. Here on the left is these beautiful laminated mudstones. Again, it's amazing that we've been able to see this, and we interpreted these to be lake deposits. And then on the right are these, again, beautifully trough cross-bedded sandstones. You can see the trough cross-bedding right here. And we interpret these to be river deposits. Outside of Pahrump Hills, as I mentioned, the rover has traversed other parts of the Murray. From images, we do know that the rest of the Murray is dominated by mudstones and sandstones. And so that's kind of shown here in the stratigraphic column. And the stratigraphic column is just a graphical representation of grain size versus elevation in this case. One of the things that we have seen is that some of these areas have, well, in sedimentology, we would call this heterolithic, but we see these rapid grain size changes and very short vertical or elevation differences. And this is really where the CAM data is really great. So that Molly camera that I was talking about, because it's on the rover arm, we actually rarely use it because it takes more energy to use that camera. And that's the camera that we need to get a grain size. However, CAM, as I said, that's the big eye of the rover. It doesn't take as much energy. And so we're constantly taking that data. And so we actually have this beautiful continuous data set from the CAM data to see how grain size has been changing in elevation. And this is really where my work has really been focused, is just trying to paint a more detailed picture of some of these grain size changes, in particular, because we do want to know how those depositional environments have changed through time. I think I've talked too much today. And this whole span that I've shown here is about 300 meters thick. But I mentioned this is actually a little old. The rover has, I think, already traversed about 400 meters worth of stratigraphy. Okay, very interested in that. And so to be able to use the Gini index to essentially interpret or estimate grain size for the Murray, I actually had to calibrate the Gini index to rocks with known grain size. And so these are some examples of those calibration rocks. And so here on the left is a fine grained sandstone, and they're, again, it's kind of hard to see the presentation, but there are individual grains here that I was able to do some detailed grain size analyses, and I know its Gini index. And then this is a coarser grain sandstone. Actually, this is a picture of those trough cross-bedded sandstones. This is actually what it looks like up close. You know, we know the grain size, and I know its Gini index. And so by determining the Gini index for these rocks with known grain size and other rocks that I'm not showing here, I was able to develop essentially a grain size scale. And so this is sort of what's shown here. On the x-axis is Gini index. And on the y-axis is actually grain size determined from images. And each point here is an individual rock for the data for one rock. And so as I mentioned earlier, the coarser you get, the higher the Gini index. We actually see this kind of plateau that happens here, but that's because of the size of the laser. It's, you know, medium sand, so we really can't say much for grains that are kind of coarser than that. This actually I've been able to develop this grain size scale, and so by just looking at the Gini index, I've been able to determine or estimate the grain size for other rocks. And the grain size scale is up here. How am I doing on time? 25 minutes. Okay. Cool. And so, so I've been able to apply that grain size, the Gini index grain size scale, now to the Murray Formation. And today, I'm only going to show you data for the Murray Formation mapped here. We actually know now that this is the Murray as well, but I'm not going to show any of that data. But this actually spans 4 years worth of data. And so it may seem like a little bit of data, but it's actually 4 years worth of data that I'm going to be showing. And this is what the data looks like. So here on the left is that stratigraphic column for the Murray Formation that I showed previously. And here on the right is this very similar plot to what I showed before. So there's Gini index on the x-axis, and then that grain size scale on the top. And then each point here is the data for an individual rock. And so one of the things that we do see is that there is obviously some grain size variability. But even with that, the bulk of the rocks in the Murray do look to be rocks dominated by clay and silt. So we interpreted those to be mudstones. Of course, we have images as well. We always take images with the CAM data. And so based on images and what we know from the Gini index data, we interpret this to suggest that the majority of the rocks in the Murray Formation were deposited in lakes, and so they're lake deposits. While the bulk of the Murray is dominated by these fine grained rocks, there's also these beautiful trends that we see here, and this is a really obvious one right here, where we see that the Gini index at this stratigraphic horizon starts increasing, and this actually, keep going. This actually correlates to a region where we saw other trough cross-bedded sandstones. And trough cross-bedding is really cool because it requires a higher energy flow to form. They commonly, these are essentially dune deposits, and they can form either by flowing liquid water or by the wind. Because we actually never got close to these rocks, we can't say which one. Because the CAM data, determines data remotely, we do know that we can correlate the sedimentary structures with the grain size, but at least we know that there's a change in depositional environment from a quiet lake environment to this higher energy environment. And so, as I just mentioned, we do see a diverse set of rocks with grain sizes in the Murray Formation. And just to kind of highlight some of this diversity, I just wanted to walk you through a little part of the section here. And so it's the same plot as before, the Gini index with elevation and that grain size scale on the top. So if we start here, we go from an area dominated by mudstones to higher Gini indices. And I didn't show this, but we actually have these beautiful mud cracks and sandstones in a particular horizon. And then at higher stratigraphic elevations, we go back to mudstones, to those trough cross-bedded sandstones that I was talking about, back to mudstones. And so again, based on what we know from images, we can make the interpretation that we possibly have lake deposits going into drying conditions to explain the mud cracks and the sandstones back to a lake environment, whether it's the same lake that dried and then refilled, or if it's a different generation of lake, we can't say that. But we do know that there was a change back to lake deposition, to those high energy environments, again, either the wind or rivers, back to lake deposition. And so what this suggests to us is that, Gale Crater had an active hydrologic cycle, and it had all these diverse environments. And so we can imagine that we had rivers emanating from the crater rim, flowing down into the lake, and sometimes there are local climatic changes with the drawdown to explain, like again, the mud cracks that I wasn't able to show. And so you can imagine that all of these deposits get preserved in the sedimentary record, and they get eroded down, and now curiosity is sort of driving through all of those remnant deposits. And yeah, Chris Fetto made this, I did not. And so to answer the first part of my talk, what environments are preserved in Gale Crater? I know this is quite quick, but we see evidence for lakes, rivers, mudflats, and maybe dunes. Some of my work actually focuses on conglomerates as well, and we interpret those to be fluvial conglomerates, and so that's cool, but that's not in the Murray, but we have also fluvial conglomerates. This suggests to us that Mars had an active hydrologic cycle with possible changes in local climate, and based on what we know about sedimentation rates for different types of lakes on Earth, and knowing that over 300 meters worth of those deposits are lake deposits, this suggests to us that these lakes were sustained for tens of thousands to millions of years, which for Earth geologists, I know that seems like a big buffer, but for us Martian geologists, that's actually a pretty good time constraint. All right, so I'm going to be transitioning now to the second part of my talk. And so now we're going from the grain size scale to the landscape scale. And for this part of my talk, I'm going to be talking about some of the work that I've been doing, or I did as a postdoc at Dartmouth, and we just recently got funded to do more of this work. And so stay tuned for more of this. But this work has focused on characterizing deltaic deposits on Mars, in particular the Gale Crater region. And as well, this is collaborative work down here. And this is an example of a deltaic deposit in the Gale Crater region. And again, this is a real image. It's not a artistic rendition. I know with the coloring it looks that way. But we can see that there is an incised valley that starts here, and then at the end we have this arcuate shaped feature here that is a deltaic deposit, and then we see this change in slope here, which we interpret to be the delta front, and this is very characteristic of deltas. And of course, on Earth, deltaic deposits form in lakes and oceans, really any standing body of water. And here are just a couple of examples. These are a pair of deltas in the Tibetan Plateau. And then here on the right is this delta that's forming in the ocean in Greenland. And in both cases, we see that characteristic arcuate shape to the deltas, which again is more characteristic of Gilbert type deltas. And then we see this even incised valley that's quite reminiscent to the feature that I showed previously. And one of the things that's pretty cool about deltaic deposits is that the front of these deltas actually can be used as a proxy for paleo water levels. So it actually represents the stable water level when that delta was forming. And so using that very basic concept, there was a previous study by another group of researchers that mapped deltas globally on Mars and interpreted them to have formed in an ocean. And that ocean would have a water level that corresponds to this magenta line here. And so this is a global topographic map of Mars. And again, we talked about the lowlands and the highlands previously, and the dichotomy boundary actually kind of corresponds to where we see that contour level. And the diamonds are the locations of those deltas. And the highest concentration of those deltas in that study are actually in the Geoid crater region. And actually, two of those deltas are actually located inside of Geoid crater. And from more recent higher resolution data sets, we now know that those deltas actually formed in, or more likely formed in paleo lakes and not in ocean. And so this is work actually that my postdoc advisor, Marissa, had done for her PhD. And so this is actually the same black and white image that I showed previously for Geoid crater. The blues here are the locations of those deltaic deposits. And then the contours are the estimated sort of boundary for those paleo lakes. And then here on the right is an example of one of these deltas called the Pancake Delta. You know, kind of looks like a pancake. And so in addition to those sedimentary rocks that I was talking about, at a later point in time, again, because water is a topographic low, water then pooled again in these younger aged lakes. And so this actually has a lot of consequences for that original other study that studied deltas, mainly because, like I said, the highest concentration of deltas from that study were in the Geoid crater region. And deltas actually have been one of the strongest pieces of evidence for the possible presence of a northern ocean on Mars. And so because of that, you know, the obvious thing to me was that, well, you know, if these two deltas that are originally determined to have formed in the ocean actually formed in lakes, is it possible that some of the other deltas also formed in lakes? And so, you might be wondering why we actually care whether the deltas formed in lakes and oceans. Ultimately, it comes down to better constraining the climate of early Mars. We actually don't have good constraints for that. And so you can imagine that if Mars had a northern global ocean, then its climate must have been either warm enough or have had higher surface pressures to be able to sustain that ocean. However, you know, if instead it had smaller lakes, then, you know, we might be able to play a little bit more with the climate conditions there. So again, it always comes back to climate and the water budget for early Mars. And so to address this, I made a ton of DEMs and used updated imagery in the Geoid crater region. And I went to identify any fan-shaped feature. Of course, if you're using imagery, it's really hard to distinguish fans from deltas, which is why we need to make digital elevation models. In my catalog, I either identified features as deltas or fans. Deltas, as we've talked about, have arcuate low gradient tops and stiffly dipping fronts, whereas alluvial fans tend to be concave up and have linear long profiles. Here on the left is actually another deltaic deposit from the Geoid crater region. And so if we take a profile over that, we kind of see some of those features that I was talking about with the stiffly dipping front. And that's clearly distinct from how we actually identify fans. And so here on the right is actually an alluvial fan in the Geoid crater region as well. And again, we can kind of distinguish both of them quite easily in topography. And of course, they also represent different depositional environments. Deltas form subaqueously, fans form subaerially. And so kind of using that, kind of going back to the Geoid crater region, this is a topographic map of the Geoid crater region. I again identified these landforms, which I'm going to show here in a minute. Right now, I'm showing the deltas from that previous study that I was mentioning. And these are the new landforms from my study, again, with updated imagery and topography. one of the obvious things that pops out is that there are a ton of these. They're everywhere. And you might see this, that a lot of them are kind of concentrated in different regions. Shown here, there's also a ton of them over here. And this trend is easier to see in plot form. How am I doing on time? 13 minutes.
15 minutes.
Oh, I went quicker than I expected. Sorry. That's great. I'll slow down a little bit. So we can actually see some of these trends a little bit better in plot form. And so here I'm actually showing longitude on the x-axis, and then delta front elevation. So the elevation of that, essentially the scarp, you know, quote unquote, for the deltas, the delta front. And one of the things that we see is that, again, they tend to kind of occur close to each other, and particularly these groups, and they tend to have very similar delta front elevations. And so here I've already kind of grouped them together. And just to give you context, this is that paleo water level mark from that previous study for that ocean. These are the two Jezreel Crater deltas that they had in that study. That's supposed to match this, just to give you a context for that difference. And so one of the things that we see is that none of these deltas actually match with that interpreted paleo water level. And so for each of these groups, we of course came to the obvious interpretation that the deltas that are occurring near each other with the same front elevations likely formed in the same standing bodies of water. You'll probably guess by now that they're probably lakes. And so if we actually take the mean of the delta front elevations, and again use the topographic data, we can make contours, and we've actually interpreted that evidence for 10 paleo lakes. 4 of the paleo lakes would have had multiple deltaic deposits. And just to give you context, this is about the size of Lake Ontario, so they're pretty big lakes. The amount of water that could have been sustained in all of these lakes is equal to 5 centimeters global water equivalent. And so this is the amount of the depth of water if it was spread out over Mars. That's how thick it would be. And as contrast for that possible inferred ocean, that's 550 meters global water equivalent. So that's quite drastic change of, again, thinking about water budgets for these water bodies in the past. In addition to this work, we've also had an undergrad do some preliminary geologic mapping, geomorphic mapping. And so essentially we just told them, hey, this is where the deltas are, go map. And independently, they were able to make this contour based on their mapping, which again looks quite similar to what we determined just using the delta front elevations that we've shown here. We also see evidence in some locations for terracing, which may be possible paleo shorelines. And the elevation of these terraces also correspond to the elevations of the delta fronts. And this is actually some of the work that we just got funded to do, is to actually do more detailed geomorphic mapping, because I feel like, you know, as a geologist, I really want to be able to prove all of this with more detailed work. And we have a grad student right now at Dartmouth College doing a lot of this work. And so kind of going back to this question, you know, do the delta deposits in the Jezreel Crater region record in Northern Ocean? The short answer is no, they likely formed in paleo lakes, essentially a series of paleo lakes. However, we of course can't say whether there was or wasn't a northern global ocean, because there are actually other features that have been proposed to support that hypothesis. Some of those features include valley networks. And so there are these channel-like features that are highlighted here in red that terminate around the dichotomy. And some people think that, you know, where else would they have flowed into if not an ocean? And so that's been used as a piece of evidence. There are also putative paleo shorelines. This is just, you know, a recent study by a friend of mine, Steve Scholes, kind of highlighting some of these shorelines. However, updated imagery has actually showed that a lot of these shorelines actually cross topography and are very clearly not shorelines. And we actually just had a paper come out, Stephen and I, talking a little bit more about that. So if you're interested in Paleo shorelines, check that out and the controversies surrounding that. That was a fun paper to write. But essentially, there's all these other pieces of evidence supporting a northern ocean. And of course, our other dichotomy deltas, right? I showed those diamonds in other places on Mars. But I don't have it here. There have been other studies by other researchers that had just came out in the last couple of months. And some deltas in other parts of the dichotomy, based on those studies, also look like they formed in lakes and not in ocean using very similar techniques. It's also possible that the lakes are remnants of a larger ocean. So you can imagine there was an ocean and it dried down. And so maybe the lakes could be remnants of a larger water body. However, if that was the case, we would essentially see the front of the deltas tracking that change in water level. We don't see that. Like I showed previously, some of the images, they just have one delta front. We don't see any obvious of progradation or progressive progradation suggesting that water level change. However, we do see that some of the deltas are directly overlain by alluvial fans, which is kind of cool. We actually see the deltaic deposits, and right on top we see essentially alluvial fans. And as I mentioned previously, they of course require different amounts of liquid water to form in different environments. And so it's possible that that might be recording a change from wet to dry conditions. Or there's just been reactivation of the catchments, that's also quite common. Kind of nearing to the end here, I did want to mention that another delta from that original study is in Jezreel Crater, which is the home of the Perseverance rover. So that beautiful delta that you probably all have seen in the news, that delta was also part of that study. We clearly know from updated imagery that it also formed in a paleo lake. But I'm still excited to see what results come out of the Perseverance rover with that deltaic deposit and getting a better sense for the water history there. And so keep an eye out for that. They've been releasing data from Perseverance a lot more recently. With that, I'm going to leave the two questions here and then open it up to questions. Thank you.
All right, we have time for questions. Let's start off with student questions. If any students have any questions.
Like any level question.
I'm just curious to know about the Gini index, like how did you estimate and what were the input parameters and how do you validate your estimation?
Yeah, so the input data to the Gini index is essentially major oxide data from the CAM-CHEM instrument. So with the CAM-CHEM instrument, you can actually determine major oxide weight percents, SiO2, iron, magnesium, calcium, potassium. And again, I don't want to get into details, it's going to get down in the rabbit hole quite quickly. But it is that major oxide data that that we then normalize and kind of input that into my code essentially that quantifies all of this. I did filter the data, and so I've been talking to people here today that in Jezreel Crater we actually have diagenetic features, and they're actually everywhere. And so if you're wondering why in some places there weren't points, that's why. So one of the things that I had to do excruciatingly as a PhD student was look at every single context image for the CAM-CHEM data to actually see where the laser was hitting, and then removing those points. And so there's this whole filtering process that I had to do by hand because, of course, I wanted to be careful. There are other quantitative measures to determine, of course, if there's diagenetic features. We know what the base weight percents for the rocks are. Like I said, we have different instruments, and so sometimes we see like 40 weight percent calcium, right? And it's just like the rest of everything around your 6 weight percent. And so we do see that in some cases they're like calcium cements. So I kind of had to eliminate like whole sections of the stratigraphy, because of that. But like I said, I'm happy to talk with you one-on-one and kind of get more into the nitty-gritty. Yeah, that's a great question. Thank you.
Yeah.
So I'm, I guess, having a bit of trouble seeing the forest through the trees because I haven't studied anything
That's okay.
with Mars before.
Yeah.
So you mentioned that Perseverance is trying to understand like early life potentially on Mars if it existed. So like, what are, I guess, what's sort of the big picture in terms of, besides water being important for life, what's sort of the big picture? Are there like specific hypotheses about life forming possibly in certain environments? Or are you trying to eventually detect fossils or bioturbation with grain size measurements? Or what's sort of the,
From my work or Perseverance?
either, but
Okay, yeah. So for Perseverance, that the main mission goal for that, I will say I'm not part of the Perseverance rover team, so take that with however you want. But I do talk about it a lot. So the main goal for that mission is to find evidence for past life on Mars. We talk about, when we say that, we're really talking about the past presence of microbial life. And so we're thinking about things like microbial mats. And so that's the reason that Perseverance has a micro XRF, is to really take those really close-up pictures to connect composition to textures. Because that's really something that we couldn't do with Curiosity. So Curiosity, we can actually, and we have measured organics, we found organics in Jezreel Crater. But because there's not that image with where the organics were determined at the really fine scale, we really can't, tie those together to really say, is there like a higher likely chance that this might be present or evidence for the preservation of things like microbial mats and like microbialites. And so that's really what that mission is focused on. It also has Raman instruments that can also be used to determine organics and other things. And so with the micro XRF is located in the rover arm for that rover. There's also a Raman instrument that's also on the rover arm, and so they're going to be able to get essentially co-located data for the same places. And then ultimately, Perseverance has drilling capabilities. It's actually acquiring cores while it's traversing and caching them along the way. And so there has been several press releases by the Perseverance team showing examples of those cores. So far, they've actually have driven mainly through igneous deposits, and it's quite clear that they're igneous. And that was a big thing before going, that people weren't sure if the crater floor there was going to be lake deposits or igneous, and they've just been seeing igneous rocks. But you can see these beautiful cores in some of the pictures that they've been releasing. And so that's the other thing that they've been doing, is coring, caching them, and then NASA has another mission called Mars Sample Return that will go back and then pick up those cores to return them to Earth to do more detailed lab analyses. And again, that's something we just can't do with Curiosity. Because again, the main goal for Curiosity was just to determine, do we have any evidence for habitable environments? And so the instruments were picked to kind of address that goal. Yeah, I feel like I'm a National Geographic.
What this go?
Yeah.
What is the primary benchmark you use to determine
The Mars Geoid that we determined using gravimetry data. And on Mars we don't have sea level, but we can use the gravimetry data to kind of determine what the Mars Geoid is, and so then everything else is kind of based from that. Yeah, and so in the strat columns, you probably noticed that they're all negative and they were getting smaller going up. Yeah. But the rovers have really accurate ways of determining location, and each instrument has its own elevation because they're in different parts of the rover. Because the rover, I didn't mention this, but Curiosity and Perseverance, they're about the size of a Mini Cooper. So you can imagine that, Cam is all the way up here, whereas some of the other instruments are, other elevations. And so each instrument has its own sort of calibration for that.
Melanie, go.
Yeah, sure. Hi.
So I guess on Mars, the atmosphere composition, the pressure, gravity, everything is different from the Earth. So, and then, Jezreel Crater is ancient. So we don't, as you said, we don't know what the ancient atmosphere must have been like.
Mhm.
How do you interpret the energy environments that would form these landforms if there are so many others?
For a lot of
what's the approach?
So for a lot of the environments that I'm talking about, everything scales. And so for you think about river environments, aeolian environments, there've been a lot of detailed studies in the lab and also numerical modeling. where if you think about the Shields diagram, thinking about shear stress with grain size, you can see that everything just kind of shifts. And so everything just scales. But I was actually talking to you before, that's, there are people who just focus on that. It's like, how do things scale? One thing that we do see is that because of the lower pressure and the grains in what we think are river deposits actually are coarser, because you can imagine that the river can actually transport it further away or on a longer distance. And so we actually see things that are a little bit coarser than we would expect for some of the environments that we're seeing. For wind environments, it's actually the opposite because of the low atmospheric pressure, because you need more energy to move particles. And so it really depends on the environment that you're talking about, but for all of it, it mostly scales. If you actually look at the equations, really what's changing is gravity, and that's usually the denominator. But I'd be happy to nerd out with you about looking at some of these sediment transport equations. But there are a lot of people that are focusing on this. So one of the great things in Jezreel Crater is that we actually have modern dunes right next to aeolian or deposits that we think are aeolian cross-bedded sandstones. And so we actually get to compare what do these things look in the ancient on Mars, and what do these things look in the modern, and we can actually see, are there differences? And so there are some people that are starting to get into that sort of level of work. That's not something that I do. Yeah.
Yeah.
Francis' question about
Yeah.
deltas. I agree that the presence of deltas is compelling evidence for deposition of standing water bodies, but just to play devil's advocate.
Sure, I like it.
Not just alluvial fans. They form subaerially, have nothing to do with standing water.
Yeah, and so for a lot of the features that I'm talking about, like I said, they all kind of are located in the same regions. And I did a lot of detailed work looking at how the elevation kind of changed throughout each landform and comparing each landform to each other. And then seeing that in these individual places, I just have a really hard time imagining that the wind would equally erode some of these features back to the same elevation. Like I have a hard time thinking about that. And of course, the profiles just don't make sense because the alluvial fans are quite low gradient. And so if you're eroding them back, just wonder how far would you have to erode back to actually get the profiles that we're seeing with some of these features. But yeah, that's a question I get all the time. But it's one of those things that the best that we can do using remote sensing data sets is just doing very detailed work. Like I said, we can see if there's any obvious evidence for gullying or erosion on the landforms. There were some landforms that I did identify that had that, and I had to take them out of my data set because it was very obvious that there was, I call it gullying, but essentially you could see that there was erosion or obvious erosion on the deltas, or you can say the features if you want to play devil's advocate. Does that answer your question?
Sounds like it's debated.
Not really, not for the stuff that I'm talking about. Commonly, I've gotten this question previously, but like I said, it's kind of hard to make sense of the data sets with what we have, but I'm happy if you have another way of testing that. You have another way of testing it? I'd be open to it, or if anybody here, we can do that.
Just to
Yeah.
follow up, what are the slopes on the fronts of these deltas?
Ooh, that I don't remember from memory. Yeah.
And it seems like that would be critical.
Yeah. Yeah.
Measurement. The deltas are pretty steep in some parts, right?
Yeah.
But they have limiting steepness. Right?
Yeah.
So you could.
Yeah. Yeah.
Assess that maybe.
Yeah, I was actually planning to have RAU students this summer to do something with deltas. Maybe I'll have them work on that. That's a great idea.
How do you, have you ruled out sort of turbidite fan process to explain what you're calling the alluvial fans?
For like in the one that I showed,
Yeah, for example.
not in my research. We do see alluvial fans all over Mars. It's not only here. They're quite common, particularly in degraded craters. And I didn't show you the best example here, but some of these are like classic,
Yeah,
like
I've seen
Death Valley
those.
alluvial fans. Yeah. But I don't know if we were talking about this. Some of my new research is kind of getting into the more alluvial fan end of things. Mostly my postdoc.
We actually have a question on Zoom. I'm
Oh,
going to
sure.
switch to Zoom here. So Amanda on Zoom says, thanks for a very interesting talk. In the figure showing the context for the Gale crater lake deposits, it looked like a lot of the top set and slope deposits near the crater margins had been preferentially eroded. What is the mechanism for eroding that part of the section? Are there any hints of where the resulting sediments would have ended up?
Wait, what? Sorry.
Yep.
Oh, if you're talking about the crater rim, maybe the crater margins. If you're listening to me, maybe you can confirm. It's the crater rim.
No, I just meant that the correlative section for the Murray Formation on the slope and the top sets which would have been more proximal to the crater rims, was eroded, and that would have been a significant amount of section potentially. So I wondered, what's, and therefore you have the, inverted topography where the lakes centered sediments are now topographically high in the center. And I just wondered, what's the mechanism for eroding that, do you think?
That's a great question. I'm laughing because this is something we argue about. Some people think it's alien. Yeah, I'd be happy to provide you some resources. There's depending on the paper you read, there's another mechanism. Yeah.
That'd be great. Thanks.
There's not the work that I do.
Yeah.
Yeah.
Heavy mineral sands, heavy channel deposits. With heavy minerals.
If there are heavy minerals in these
Channels.
in the channels. And so with CAM, because it does shoot the laser, we actually can determine the grain or the composition of individual grains. But I don't think anybody has actually seen it.
Magnetite, monazite.
Oh, if we see that. So we do see magnetite and all sorts of iron oxides on Mars, but we actually haven't seen anything correlating to that. We actually, Chris Feddo's on the team, is something that he super is focused on, is physical and chemical sorting in rivers, and he's been trying to look for that, and we actually haven't seen anything like what you're talking
That
about.
would be a normal thing on a good channel.
Yeah. Yeah, I agree. Yeah. But yeah, at least I haven't looked into it. Like I said, there's a geologist on the team that his whole research, a good chunk of his research is kind of focused on that, and we haven't seen anything like that. But we do have iron oxides on Mars. Most of Mars is basaltic, and so it's actually everywhere. The dust of Mars actually has a lot of magnetite and hematite. And we do see that in the actual layers, but I haven't seen anything where you see heavy minerals preferentially in one horizon over another.
We had a meandering stream, like we find heavy minerals.
Yeah. I've seen that. Yeah, but we actually haven't seen anything like that, at least to my knowledge. But unfortunately, with Curiosity, this is one of the things. As a geologist, it's just the rover only goes in one direction. It's really rare when the rover goes left or goes right. Only in the places that we stay multiple days. That's really when we start exploring a little bit more. And so these stratigraphic columns are truly just a stratigraphic column, along one direction. You could probably have seen that in the traverse. And so we actually don't know we don't actually have a lot of information like the lateral continuity of some of these depositional environments. It's possible that instead of one major lake inside of Gale Crater, there could have been these potentially separated lakes. Or, when you're talking about these streams, we're only getting a quick snapshot of some of these environments. And it's really frustrating.
We have time for maybe one last question. Yes.
I was wondering because I know we talked about the crater rim of it, but I was wondering if you see any instances of these old impact features kind of interacting with where the water erosion occurs.
If there are actually craters inside of a crater with some of these deposits.
Yes, or just any kind of scarps or anything in controlling where the erosion.
Short answer is yes, in some locations, but not where the rover's driving. We have seen, kind of hard to see in some of the pictures that I showed, but inside of Gale Crater, there are a ton of craters, right? And that's actually how we determine the age of Gale Crater, is by doing crater counting inside of the crater. And every so often, we actually do see these craters from the distance. And so that's been pretty cool, is actually seeing some of these craters on the ground. But we rarely, like I said, we kind of rarely kind of explore some of those. But we do see evidence for things like that, yeah. I'd be happy to show you this. They're pretty cool. You can actually see the, you know, the rocks that probably were moved from the crater. You can see the little the rays. And you can even see dunes inside of the craters that are inside of the crater. It kind of gets, you know, like the Russian doll sort of situation quite quickly. Yeah. Does that answer?
All right, let's give a round of applause for the speaker again.
Graduates and friends, if you would like to join us, we'll see you up at the top.
Okay,
I am taking that idea from my RADO students.
thank you.
That's a good idea.